Good morning all. In last lecture I have stopped in this slide, that is the inverting amplifier, gain of inverting amplifier expression. So your gain of inverting amplifier is the ratio between your output voltage and input voltage. Your output voltage we have derived for the output voltage, and the input voltage is V1. So output voltage is V1 into feedback ratio of feedback resistance to your R1. That is what mentioned here. So your V1 into, that is input voltage, into your ratio of feedback resistance to the input resistance R1. So V divided by your input voltage, that is, so V1 get cancelled, and I have included the negative sign over here, and this negative sign denotes the output voltage is out of phase with respect to the input voltage. It is out of phase with respect to the input voltage by 180 degree. That is what the negative sign represents. Suddenly the negative sign comes because your output voltage will be out of phase with respect to your input voltage by 180 degree. That is why I have included a negative sign over here. And the final expression for your gain voltages is the ratio of feedback resistance to the input resistance. And thus the closed loop gain of inverting amplifier is proportional to the ratio of feedback resistance to the input resistance, and gain of amplifier is varied by varying this resistance, these resistance values. As I said earlier, the negative sign denotes the out of phase of your output voltage with respect to input voltage, or its opposite polarity. And the output voltage can be controlled by varying the input voltage. That is why this type of amplifier is termed as voltage controlled voltage source. And coming to non-inverting amplifier, here the input, inverting side is grounded, and the input is given to the non-inverting terminal. That is why this type of amplifier is termed as non-inverting amplifier, and input signal is applied to the non-inverting terminal, as I said earlier, and the circuit amplifies without in the inverting input. The inverting input is grounded, and V1 is made 0. And this type of amplifier is called as non-inverting amplifier. And to analyze this type of non-inverting amplifier circuit configuration, a linear negative feedback principle is used. What is this linear negative feedback principle is? The input voltage are made equal, that is V1 will be equal to V2. So at this condition is referred as, when V1 is equals to V2, the condition is referred as virtual short. That is, the amplifier is doing the differential function, so your differential voltage will become 0. So now the ratio of now the feedback resistance and input resistance R1 will form a potential divider. This is resistance R1. This form a potential divider. So the input voltage value with respect to output voltage becomes output voltage divided by R1 plus R2, that is input resistance plus feedback resistance into your input resistance, gives your input voltage. So as in the previous inverting amplifier itself, I have said there will be no current flows through the operation amplifier. So your output voltage divided by input voltage, from this equation, from this expression, it is rewritten as R1 plus RFP, that is input resistance plus feedback resistance divided by input resistance. This can be rewritten as 1 plus, that is R1 and R1 get cancelled. So 1 plus R1 divided by RFB, that is input resistance divided by feedback resistance. And the gain, voltage gain is AC, is given by output voltage divided by input voltage, as seen in previous expression. So it is equal to 1 plus R1 divided by RFB. So here the output voltage V0 is obtained in phase or polarity with the input voltage. That is, there is no change in polarity or change in phase occurs in this output gain, so it is in positive sign. And here the gain is always greater than unity, that is greater than 1, and voltage gain is adjusted by unity or more by proper selection of resistors. So we can vary the voltage gain by varying the value of resistance, that is your feedback resistance and input resistance. And in non-inverting amplifier also, as you change the input voltage, your output voltage is going to change. That is, it means the output voltage is proportional to input voltage. So this configuration is also termed as voltage controlled voltage source. And that ends your operational amplifier topic. And here's a new topic: digital to analog converter. This term we often hear. So digital, that is, we are going to convert the digital signal into an analog signal. Analog signal is a continuous signal. Digital signal is a discrete signal. And in this application of a digital to analog conversion is used in instrumentation systems. That is, before processing before being processed through the computer driver display. We use this digital to analog converter before for displaying the digital quantities into an analog signal. And here is the basic block diagram of your digital to analog converter. We have digital inputs D1, D2 up to Dn we have, and one analog output with positive and negative sign. And also we have given a reference voltage VR in order to obtain the analog voltage, and this is what is mentioned here. And VR is nothing but reference voltage, and VO is output voltage. And here the input in the n-bit binary word is combined with the reference voltage. That is, the binary word is combined with the reference voltage in order to convert it into a analog signal, that is continuous signal. And the output of digital to analog converter will be either a voltage or current. It is going to give voltage or current as the output. And output voltage of n-bit your digital to analog converter is given by, that is output voltage, it is mentioned as V0, which is equals to the product of your reference voltage into sum of your discrete signals with that is what is mentioned here. So VR into D1 into 2 power minus 1 plus D2 into 2 power minus 2 plus etc. up to Dn into 2 power minus n. So where VR is the reference voltage, D1 is your MSB with the weight of VR divided by 2, and that is the voltage with respect to the weight of VR divided by 2, and D2 is LSB, the low system band with the weight of VR divided by 2n. And D1, D2, D3 are n-bit binary words. And there are different types of digital to analog converter. One is binary weighted resistor digital to analog converter. The second one is R2 to R. That is, these resistance is alone used over there. That is why it is termed as R to 2R ladder. It is going to also form a ladder structure. That is why it is termed as R to 2R ladder, and inverter R to 2R ladder. These are the different types of digital to analog converter. We are going to see binary weighted resistor and R to 2R ladder in detail in the following slides. Your binary weighted resistor DAC is it uses operational amplifier to sum up the binary weights currents derived from the reference voltage, and via the current scaling of resistors will be 2R, 4R, 8R, that is that will be up to 2 power n into R. That it goes on increasing based upon the number of bits. And here we are giving a supply, and it is given to the resistances through switch to the the input signals were obtained and it is connected. So if the switch is closed, it is going to be form a binary digit 1, and if the switch is open, it is going to form a binary digit 0. And the input is this input signal is given to the operational amplifier with the feedback resistance, and output is obtained. This is how your binary weighted digital to analog converter circuit looks like. And here the switch positions are controlled by digital inputs. Only two inputs will be there. We know the digital inputs will be of binary ports 0 and 1. So when input is 1, the switch is closed, and 0, the switch is open, as I said earlier. And then operational amplifier, here the amplifier is doing the summing operation, whereas in inverting and non-inverting amplifier we have seen the differential operation. Here the amplifier is doing the summing operation, and due to high input impedance of operational amplifier, summing current will flow through the feedback resistor RF. And now the total current is IT. IT represents the total current, which is equal to sum of the currents that is present in the circuit, that is I1 plus I2 plus I3 plus etc. up to IN. And the output voltage is the voltage drop across your feedback resistance, and it is given by Vout is equals to minus total current into your reference feedback resistance, and this will be equal to, we know, total current is equals to I1 plus I2 plus I3 plus etc. up to IN into RF. So the value of I1 is your input voltage, input binary code D1 into your VR divided by 2R, the resistance, voltage into resistance corresponding to it. and D plus D2. Similarly, for other currents, we have substituted the values, and up to it is substituted up to n values. So we are taking VR by R as common value, and your equation becomes like this. That is minus VR divided by R into d1 into 2 power minus 1 plus d2 into 2 power minus 2 plus d3 into 2 power minus 3 plus etc. up to dn into 2 power n into your feedback resistance. So when your feedback resistance will be equal to input resistance R, then what happens to your output voltages? Your input resistance, feedback resistance get cancelled. So your term your output voltage will become minus VR into d1 into 2 power minus 1 plus d2 into 2 power minus 2 plus d3 into 2 power minus 3 plus etc. up to dn into 2 power minus n. So from this equation, we might conclude one thing, that analog output voltage is proportional to digital input data. And that is what about your binary ladder, binary weighted resistor digital to analog converter. And in R to 2R ladder, as I said, from the diagram itself you can understand we are going to use only two types of resistance. One is R and the other one is 2R. And this structure looks like a ladder. That is why it is termed as R to 2R ladder. And this gives the diagram. We are connecting the 2R and R circuits in parallel with each other, and to that resistance we are giving the input binary codes here. And here we have mentioned a 3-bit digital to analog converter. That is why I have added this number of resistance to the circuit, and we have already added one more 2R resistance. This is nothing but your feedback resistance, which is given to the amplifier, and this is grounded. And the input of the ladder network must be a switch from the voltage representing voltage representing 1 and ground representing 0, and it should be never left open circuited. It should either grounded or it is closed. It should never be open circuited. And the resistors which are loaded remains same for all bits of digital input. The switch position D1, D2, D3 corresponds to the binary word 100. Why? Because your switch one is alone closed and the other switches are open. That is why it terms as 100. And we are forming the simplified equivalent circuit in this slide, and we are simplifying the circuit, and finally the equivalent circuit will be like this. That is between the voltage and ground, it forms a 2R and 2 by 3R, and the derivation is over here. So the equivalent resistance at node A, and here is node A. So here equivalent resistance is 2R is parallel to 2R. So I have done the parallel operation. So 2R by 2R is equals to 2R into 2R divided by 2R plus 2R. That is R1, R2. If R1 and R2 are in parallel condition, then the parallel formula is R1, R2 divided by R1 plus R2, which is equals to R. Similarly, I have simplified all, the circuit through. I have simplified all this circuit, and finally I obtained the equivalent resistance as 2 by 3 into R. This is what the input resistance I obtained. So output voltage at node C is calculated by. So the voltage, what is the voltage at node C is your output. VR into 2R by 3 divided by 2R plus 2R by 3. So it will become. A simplification process is done, and finally it is given as minus VR divided by 4. So your output voltage will become, which is equals to minus 2R by R into minus VR divided by 4, which will become V0 is the output voltage is equals to your reference voltage divided by 2. So the output voltage of digital to analog converter is proportional to the sum of weights represented in switch. And the advantages are, it is going to have high resolution, high accuracy, and it requires only 2 value of resistance. That is the main advantage of this type of R to 2R type of ladder digital to analog converter. And for every input, only 2 and R and 2R resistance is alone used. So here I end my lecture for your